All right, so let's go ahead and get started. You're passing out a roll sheet for your assigned seating and all that good stuff. Jacob's passing that stuff out. The other thing is you got a homework set due for me today. So, and I brought my stapler because I don't believe you people actually have heard of one, more or less own one. So with all the different pages you should have printed out, so please use the stapler and pass it out, and then pass the papers to your right, and we'll come up here and pick them up and stuff like that. But I did bring a stapler for you today. Don't bank on that every time. Couple of questions for you guys. Most of you guys have done the, there's the traditional homework set, which is due now. The actual homework set, which is from the online homework set, is due tonight at 11:59. But looking at my data sheet, most of you, not all, but most of you have already completed that homework set. Question for you. Now, it's different from the traditional homework set. How did you like the online homework set? Good examples. You're right. This is why I did that unlimited thing. So if you like try it 3 times and still don't get it, you got a way of showing the explanation, and then they will give you a different kind of a problem, and you can still get the point totals out of it and stuff like that. So again, this is classic online book rep type of stuff. So again, and I always make the online homework set due the same day as the traditional one, but I usually set it at 11:59. So if you haven't finished it yet, you've got until 1 minute before midnight before it closes out on you. But it will close out on you. So there's a couple of folks in here, according to my data now, that haven't even purchased or done the getting the book and all that stuff. When I sent you guys the information about exactly how to do that through the Canvas site, so it's a quick link, so you should have quick access to it. So if you are procrastinating, it will bite you in the rear end at the end of the day. So get onto it, because if you also pay attention up here, let's go over here to assignments. I guess it's easier for me to look at this one right here. What have I already got up for you? What is this thing right here? Homework number 2 online is up, and your traditional homework set for the rest of 1.5 through 1.10 is also up waiting for you guys. And this one I set for the 15th. Say you got, what, a couple of weeks on this one? Week and a half or so to finish up these particular homework sets and stuff like that. So I've already, since you're doing homework number 1 was due today, you notice immediately I turn on homework number 2. And then after homework 1 and 2, because people ask me about, well, after that, when is our test scheduled? Soon thereafter, okay? So we're looking at, I think this was due on Thursday, the 15th. It will be on that following Tuesday is when I plan on having your next test. I will post more information about that, but it's right after you've got all your particular material and stuff like that up. And these homework sets, especially the traditional ones, are the best review for your test. I would recommend also going back and looking at the online ones once I set that up for you guys to do that. But the traditional ones are your best ones because it's a traditional test. Yeah.
You said the test would be probably, it would be after September 15th?
Yeah, it'll be that following Tuesday, whatever that is. You're going to ask me that question. Okay, let's go to a calendar. The 15th is due within pretty much a week and a couple of days, so we're talking about 2 weeks, the 20th. All right, that's my plan. All right, so let's go ahead and get started on today's awesome lecture. And that is, again, I'm doing basically word problems for you guys today. But before I get to the word problems, again, I want to talk about the idea of solution sets and how things fit together. And I talked a little bit about this last time, but from there I kind of want to hit the particular questions and stuff like that. So, because we're doing basically today 1.6, I'm going to dabble into a little bit of 1.7 today, and 1.6 on applications. You know, another word for applications in a math textbook means word problems. So we're going to be doing some word problems today, but turning those word problems into a system of equations so we can actually solve these guys. And there's 2 different types that I want to talk about: economic types and civil engineering inflow, outflow types. and stuff. So, again, I've got lots of examples for you guys and stuff. So let's start off with today's awesome lecture, and that is this. Again, one I wrote up last time, but again, want to talk about it. Theorem. If you have this matrix equation, AX equals B is consistent for some B, and P is a solution called a particular solution of this equation, AX equals B, then the set of solutions is of the form W is equal to P plus Vn, where Vn is the solution of the equation AX equals 0, the homogeneous equation. So, and this goes back to the folks that have had differential equations, and if you haven't, well, something else for you guys to look forward to. How do we end up looking at solutions to systems of equations? And traditionally, we're going to look at them in vectored form, and in the vectored form, you're typically going to see two types of answers. You're going to get something called a particular solution that actually solved that equation AX equals B, and then plus you're going to get this arbitrary solution that solves the homogeneous equation, which is the AX equals 0. And it'll be put together as an actual solution set. So note, AX equals B, AX equals 0 has only the solution X equals 0, then the solution for AX equals B is going to be unique, and it will be just that P vector equation, that particular solution that solved this guy. So if you get X equals 0 is the only solution that solves the homogeneous, well, add 0 vector to any other vector, you get any other vector back again, and you're only going to get the P vector. But if you got an infinite number of solutions, consistent infinite, you're going to get that homogeneous equation, which is called under the Vn, and the particular equation that actually solves the AX equals B. So to show you an example of that, I want us to work together and solve this guy as a system of equations, okay? So, here we go. How are we going to solve this guy? Let's work this one together because it's the beginning of class and you've had a long weekend. All right, so, first things first. I'm going to write this as an augmented matrix. So writing it as an augmented matrix, I get 1, 3, 1, augment 1, negative 4, negative 9, 2, negative 1, 0, negative 3, negative 6, negative 3 augmented there. Does that make sense so far? Okay? Now, what's my next move? I want to go for RREF. What does RREF stand for? Reduced row echelon form. I want to take this thing down to what it's really supposed to look like, that unique solution thing. So I went ahead and put the pivot up there in the top corner here, first row, first column position, and I'm going to sweep down and make some zeros. So I'm going to take 4 times row 1, add it to row 2, replace row 2 with it, and then I'm going to, already got a 0 already down here, so there's not much more I need to do. So when I do that, I get 1, 3, 1, augment 1. Now 4 times this plus this. 4 times 1 is 1 plus negative 4 is 0. 4 times 1 is 4 plus negative 4 is 0. 4 times 3 is 12 minus 9. 12 minus 9 is 3. 4 times 1 is 4 plus 2 is 6. 4 times 1 is 4 minus 1 is 3. And this is 0, negative 3, negative 6, negative 3. What's your next move?
Combine rows 2 and 3.
Right, okay, so this was a pivot and I got zeros below it. Now I want to make this guy a pivot. It's typically what I would do, because if I divide by 3, I'm not going to make fractions. So let's go there. So this would be 1/3 times row 2, basically. This would give me 1, 3, 1, augment 1, 0, 1, 2, 1, and then 0, negative 3, negative 6, negative 3. Then I'm going to do sweep down and make zeros. And I'm doing this because I'm trying to be consistent in terms of my application. Question?
Could you just go ahead and combine rows 2 and 3?
I could have, absolutely. If you wanted to do that first, that's fine. But traditionally, I make pivot, make him a 1, make zeros below. Pivot, make him a 1, and make zeros below him. Pivot, make a 1 here, and then sweep up, make zeros above him. I'm doing the pattern, but if you can do it quick and add two rows together, make some zeros, go for it. Yeah.
So in this case, the ones that are distributed well include 6 and 3.
Exactly.
If that wasn't the case, and it
Then I would
wasn't
have added the two
divisible,
rows.
you would just skip down to the next row.
Right, I would have added the two rows together, but eventually, if I want reduced or echelon form, I am going to have to go back and make them fractions. But I typically want to make fractions one of the last things I do for the chance of making bonehead careless errors. So, here we go. This will be 3 times row 2 added to row 3, replace row 3 with them, and this will give me 1, 3, 1, 0, 1, 2. Let's see here, augment here, 1, 1. And then here we go. 0, 3 times 1 is 3, plus negative 3 is 0. 3 times 2 is 6, plus 6 is 0. 3 times 1 is 3, plus negative 3, a row of zeros, okay? And then I got one more move to make. Because there's no pivot down here, I'm going to do this pivot, REO1, I'm going to sweep up, so this will be negative 3 times row 2 added back to row 1, replace row 1. So when I do that, this will give me what? 0, 0, 0, augment 0, 0, 1, 2, 1, and here we go. 0 times negative 3 is 0, plus 1 is 1. Negative 3 times 1 is negative 3, plus 3 is 0, that was the point. Negative 3 times 2 is negative 6, plus 1 is a negative 5. And negative 3 times 1 is negative 3, plus 1 is a negative 2. Double check my basic arithmetic skills, okay? Did you guys get that? This, and again, something I'm going to ask you guys questions on test like, this is in RREF. How do you know? Well, I look for the pivots, and above and below the pivots, what do you see? Zeros, and the pivots are ones. In REF, pivots don't have to be ones, but in RREF, reduced or echelon form, the pivots have to be ones. Question? Second line, this would be in REF, yes. REF, you only have to have zeros below, you do not have to have zeros above. Does that make sense? So you're right, this one would be in REF, the rest of them are in neither, okay? Yeah. RREF, this is in reduced or echelon form. This one is actually, as we were just discussing, is in REF form. Because you don't have to have the pivots be one, but they are. But you all, for REF, all you got to have is pivots, not necessarily ones, but you got to have zeros just below them. Okay? But in RREF, you got to have pivots to be ones, and they got to be zeros below and above, and that's what makes it a unique solution. All right. So now, let's write the answer. Remember what the question was. This was the question, right? System of equations. I want you to write it, listen to my words, in parametric vectored form. Write this answer in parametric vectored form. To write it in parametric vectored form, the first thing I'm going to do here is rewrite it as equations. Remember, this is the coefficient matrix of x1, x2, and x3. So this would be x1 minus 5x3 equals negative 2. And the second equation is going to be x2 plus 2x3 is equal to 1. That's it. This row of zeros is 0x plus 0, x1 plus 0x2 equals 0. Who cares about that? No reason to write the zero equation. Okay? Now, I want to convert it into parametric form. To parametric form, I want to solve for the pivots. Who are the pivots? The pivots are the x1 and the x2. These are my pivots. So this tells me that I have x1 is equal to, add 5x3 to the side, 5x3 minus 2, and x2, move the 2x3 to the other side, will be equal to negative 2x3 plus 1. I'm moving them to the other side. I'm solving for the pivots. Solve for pivots. Does that make sense? To put the equations in parametric form, x1 is 5x3 minus 2, x2 equals negative 2x3. These are pivots. However, x3 is called a what? He is a free variable, and free variables are always equal to themselves, x3. This would be the answer in parametric form. Does that make sense? But that's not what I asked for. I asked for parametric vectored form. So, to be in parametric vectored form, you're going to write this as a vector. The x1, x2, x3 is a vector. It'll be x1, x2, x3. This is also known as your x vector. Okay? That is equal to, you pull out the coefficients in vectored form. This would be 5, -2, 1. That is multiplied by x3 plus, you've got your constant vector over here. What is this? -2, 1, and there is no constant down here. So what are you going to put? A 0. Does that make sense? Did I lose you guys anywhere? Now, I want to go back and look at this statement right here, okay? Looking back at this statement, we're talking about any solution of the form of AX equals B, which is really what you got here in your augmented matrix form. You could write this as a matrix type thing here. Your solutions are going to look like a particular solution plus a solution that's a sub H there. That is what we call the homogeneous solution, okay? So if I look at this thing, I want you to see this. This is your constant. This is the P, or particular solution. Okay? It is the vector -2, 1, 0. That actually solved the actual equation. This is the free variable one. This is the homogeneous solution. So when you look at these two particular vectors type thing here, this is the the homogeneous solution plus the particular solution. That's what gives me the general solution to the non-homogeneous equation. This was a non-homogeneous equation. If I write this as matrix A times X equals B, you would write this as 1, 3, 1, -4, -9, 2, 0, -3, -6, multiplied times the vector x1, x2, x3. It would be equal to the B vector 1, -1, -3. So system of equations, matrix equations. The point is, in parametric vectored form, you'll get the homogeneous solution. The homogeneous solutions are the ones with the free variables attached to them, and your particular solution is the constant solution. That's what solves the particular solution for it's a non-homogeneous equation. This is what the theorem is telling you. Any solution is going to be the solution part will be broken up into two parts, the homogeneous part and a particular part for any non-homogeneous solution. Yeah. Yeah, if this one is, if you got a unique solution, that meant that this part didn't there, and you would have only one solution to it. And here's the deal: if you only had one solution, a unique solution, then the homogeneous, the only thing that's solving the homogeneous is x1 had to be 0, x2 had to be 0, x3 had to be 0. So that would make this vector go away, and then you only get the particular solution is the only solution. And that's what's being said down here. If AX equals 0 has the solution of x equals 0, so you don't get any free variables, okay? Then the solution AX will be unique, and it will be just that particular solution. Does that make sense? So again, tying it back into what we're going to do later on in life, like differential equations. When you've got differential equations, you can look at differential equations as homogeneous. You're going to set second order differential equations equal to 0, and then you're going to take second order differential equations and set them equal to what we call a forcing function, and the solution set will look exactly the same. You'll have a homogeneous solution plus a particular solution. That's how the solutions are broken up in the world of DPQ. It's very, very similar. All right. Question. All right. So moving on. Again, just to make, again, I mentioned this to you guys when I first started this stuff, that this class is called Introduction to Linear Algebra. It doesn't matter what class it's called. When you got the word Introduction to, you're going to get a lot of terminology, a lot of definitions. So I want to make sure you understand that terminology and definitions. You probably saw a lot of that terminology as I was giving you, even on the traditional homework set, some of those questions at the end about overdeterminate, underdeterminate, those type of things and stuff. It's all about understanding the definitions of the concept. Whether I teach you guys introduction to modern or abstract algebra, we first start out with a bunch of definitions. Introduction to differential equations, we start out with a bunch of definitions. Same idea with Introduction to Linear Algebra. Okay? So, when I say I want it in parametric form, this is what the answer looks like. You write equations. X1 equals, free variable minus something or other. X2 equals free variable times something plus something else. X3 equals, X3 is the free variable, it equals himself. This is what a parametric form is. Rewriting this guy in terms of a parametric vectored form, rewrite it with vectors. So vector X would be X1, X2, X3, as seen in the last example. That would be the coefficients -4, 3, 1 as a vector times the scalar or constant X3 plus -5, 3, and the free variable X3 equals X3, so there is no constant on that guy, 0. And again, what's going on here is the ones with the free variables is called the solution to the homogeneous part of your linear equation. And this answer over here is your particular solution. So the particular solution that actually solves the non-homogeneous part, this is the one that actually solves the AX equals B plus any scaling constant of the homogeneous solution. But what's going on from a visual perspective is this is your answer, but to solve a non-homogeneous, this particular solution is a shifting of your answer. It takes this guy and kind of slides it over to get the infinite number solution type thing here. So what does this actually mean? You basically have this. This is your homogeneous solution. So this vector here goes through the origin, 0, 0, 0 there. Okay, AX equals 0. So to solve this AX equals B, you're going to take this solution, and with that particular solution, slides it up or shifts it to get the solutions on this guy. You'll notice they are, quote, parallel. Now again, I'm talking in a two-dimensional shape. I could also draw this three-dimensionally and talk about parallel planes actually looking something like this. But after 3 dimensions, once I go into X, 4 dimensions, R4 or R5, it's all now theory because I can't quite draw an R4 and an R5 type of system here and stuff. So you get a feel for what's exactly going on. So I kind of drew this two-dimensionally that here's one vector that it goes through the origin. So this is going to be the solution to the homogeneous equation. So adding that particular solution to it just slides it up or scales, shifts it over, and that's where you get your shifted answer from for the non-homogeneous equation and stuff. So big theorem down here, again, says if AX equals B is a consistent for some B, and P is the solution for the particular solution for the AX equals B, then the solution set of the form W equals P plus VH, where VH is the solution of AX equals 0. So every answer on a non-homogeneous solution has the idea of a homogeneous part of the answer plus the particular part of the answer. That's what I'm trying to emphasize here. Question?
What is that non-graph, like to the very right, what does that say?
To the graph here.
The one after the homogeneous, correct?
The answers are parallel. And that's what I'm kind of referring to this. And that's why I mentioned parallel lines, or if I do 3 dimensions, it's parallel planes. Or once beyond that, R4 and R5, it gets kind of tough to kind of draw that. But the concept is it's shifting, it's parallel. Okay? And if AX equals 0 has the trivial solution, X equals 0, the only thing that solves it, then the solution of AX equals B will be a unique solution. And it ends up being that particular solution that actually, as you said, it will be only this solution at all, as the only solution that works. So you get this infinite number of solutions versus that unique solution aspect of this thing. When you get a unique solution, that meant that solving the homogeneous equation setting equals 0, the only one answer that solves that, which is the 0, 0, 0 vector. Only X equals 0 is working for that. All right, so moving on. And I grabbed a problem out of the textbook here, so I'm going to show you my textbook up here real quick. And I'm looking at basically homogeneous problems in economics. This is section 1.6 from our textbook and stuff. So applications of linear algebra. So, and I'm going to go through this pretty much the general part of this example 1 right here, and then I'm going to rewrite it for you. Okay, suppose an economic system consists of coal, electric power, and steel sectors, and the output of the sector is distributed among the various sectors shown in table 1. We'll take a look at that in a second. All right, so And again, I'll throw in my example up here and start referring to you. So this is called an exchange model. So let me show you this. This is easiest type because typically we give you the matrix for it. So Merry Christmas on that one. But here it is. Economics exchange model. When you're talking about an economy of a system, you're looking at particular variables that go into the system. They go into the system and they also are generated by the system. So this is that economic model that we're referring to. So economic models are divided into sectors, and for each sector we know something or other. We know the total output for 1 year. Typically we like to look at these sectors being analyzed over a year's period of time. And we know how output is divided or exchanged among the other sectors, how the interaction is. So if I'm looking at steel, you know, we're going to have to use some electricity, we're going to have to use some coal on that to be able to produce more steel, but with that we may be able to produce some more electricity with some of the generators that we're using or whatever. So there's this exchange model going on here. Okay? And of course, we're talking about economics, so our number one concept of economics is going to be money. So we also know that the price of an output, the total dollar value of an output, okay? So we're looking at monetarily how this economics, this exchange model exchanges. And what we're looking for is, what is the solution that's going to be the best outcome for all parts that are involved in it? So that special outcome is called the equilibrium or equilibrium prices. Then there exist equilibrium prices that can be assigned to the total outputs of each sector such that the income balances the expenses. You got money coming in, you got product coming out, money also coming out with these products. We want to have that happy medium where everything balances itself out. That's called the equilibrium. You guys would know it better as the solution to the model. So, in that problem that I just showed you guys, here is the matrix that they gave you. All right. So this is inputs, this is outputs. So I kind of rewrote my model up here for you from that example from the book. We got input needs. All right. So I've got to read my handwriting here. That is the word coal. Okay. So we have coal, electric, and steel. That's what we're focusing on here. So let me blow this one up. You guys can see this in the back a little bit better. All right. So we have coal, electric, and steel. That's the output, and we have the input, which is steel. Same order. Order is important. Coal was first, coal will be on the top. Electric is second, electric's in the middle, steel is third, steel will be on the bottom, okay? So we have coal, electric, steel, and we have coal, electric, steel being our output needs. So here's the deal. We know that when you're actually playing around with coal, when you get coal, there's no output. We're going to be basically using and eating up all the coal. So the output of coal, you don't get any more coal out of that. But from that coal, 40% of the coal that we use in our economic system is going to make up the help us with our electric model, okay, using to generate electricity. 60% of that coal is going to be used to help us deal with the steel industry and heating up the steel to be able to make the products and to kind of basically refine the materials to make our steel. Okay? So, the electric model, okay, our purchase by electricity. We know that when we're dealing with electricity, 60% of electricity is being used up by the coal industry. Believe it or not, electricity will generate some electricity, so even though we're using electricity, we can still use electricity to generate more electricity. 10% of electricity, and this is what I call the expense to electric, so 10% is going to go right back into the electric model there, and then 20% of my electric model is going to be used in the steel aspect of my economics of my closed system here. And the last one is steel. Out of the steel, 40% is used in the coal industry. 50% of the steel that we're using is going to be outputting on the electric, and 20% of the steel is the expense to use steel will go right back into the steel industry. So you have this exchange of using steel to make more steel type of aspect of it stuff. So, quote, So these columns here is how the output is divided. So in the outputs of coal, 0% of coal goes right back to coal, but 60% of coal is used in the electric world, 40% of coal is used in the steel world. Electricity, 40% of electricity is used in the coal industry, 10% electricity is basically the expense to get more electricity out of it, and 50% of electricity is used in the steel industry in our closed model. And steel, 60% of the steel is going into the coal, 20% of steel is going to electricity, and 20% of the steel is going back into the steel industry as it cycles back. So our goal here is to find the prices in dollars of the total annual outputs of the coal, electric, and steel by, I'm going to code this as PC, PE, and PS. P is price, so don't think too deep in our stuff. C is coal, E is electric, and S is steel. Okay, there you go. Is it possible to find an equilibrium price? Question.
What is the small, like the other one, so I said how divided with the other two small ones say?
This one right here,
Yeah.
expense to electric, this was electric back to electric, expense to steel, steel back to steel. So you're getting, with coal, you didn't have that, putting in coal creates more coal. We don't actually create more coal. But with electricity, we can use electricity to create electricity. We can use steel to help create more steel, stuff like that, okay? So, turn my page over here. Now, from this, I want you to see where the equations come from. So maybe I should do it this way, okay? I'll put my equations up underneath this guy. All right, so here we go. And I want you to see this. So, the price of coal, so I'm putting it like equal to over here, is equal to 40% of the price on electricity plus 60% on the price of steel. So you get the equation right here. So this is PC equals 0.4 times PE plus 60% 0.6 times PS. Price on electricity, that's going to be equal to 60% 0.6 times PC plus 10% times PE, so you get PE back again, plus 20% times PS, okay? This is from row 2. The rows are the equations in these electric, or in these exchange models. The rows are the equations, okay? And then continue on. The price on the steel, well, where do we get the steel from? We get 40% of the price on coal, plus 50% on the price of electricity, plus 20% back on the price of steel, because again, you can use steel to create more steel in terms of the model that you're creating here. Does that make sense? Do you see how we went from the matrix to the equations? So now, with that being said, slide it up here so you guys can see this. Pull this out of the way. How would I solve this thing? So let me pull this over here so I can actually have something to actually solve. How would you solve this thing? Now, we're talking about a system of equations. You're thinking you should automatically go for a matrix. Here's your problem. This is what you want to pay attention to with these type of problems. There is no extra constant on these things. This is a closed economic system. So all you've got is 3 factors: coal, steel, and electricity, right? So, because you've got, for example, PE, price on electricity here, and PE over here, what you should do is you should combine variables. You only want to have one variable with an equation. Does that make sense? Which, in other words, you want to set this guy equal to 0. Create this homogeneous, trying to find this equilibrium state. So, if I'm going to do this, I'm going to pull all these variables over here to the left-hand side. So I'm going to subtract PC from both sides. This will give me negative PC plus 0.4 PE plus 0.6 PS. And that would be equal to 0 because I moved everything to one side. Does that make sense? This is the trick on how to do these economic problems. On this one, I'm going to set it equal to 0. So this is 1 PE. I'm going to move it over here. And what do I end up getting? And they try to line these guys up. This would be 0.6 PC. But if I take 0.1 PE and move to the other side, that'll be 0.1 PE minus 1 PE. That's a negative 0.9 PE. Does that make sense in terms of what I'm actually trying to do without actually writing on top of everything? I moved this to the side. I subtracted 1 PE from both sides. And then I combine variables. What is 0.1 PE minus 1 PE? Negative 0.9 PE, okay? And then I get a plus 0.2 PS equals 0. And notice my variables are lining up, systems of equations. What about this dude here? This is PS equals 0.4 PC plus 0.5 PE plus 0.2 PS. I'm going to subtract the PS from both sides. That would give me 0.4 PC plus 0.5 PE. And then I subtract 1, that'll be minus 0.8 PS. And that would be equal to 0. Does that make sense? This is, you got these equations which came from the exchange model, written typically in a matrix style format. But then you got to convert it to an equation, this, so you can actually end up solving for it. Does that make sense? Now, does there exist an economic model on this particular guy is the $64 question here. So, what are you going to do here? Well, I'm going to convert this into a matrix. This would be negative 1, 0.4, 0.6. Now, I'm going to do an augmented matrix, but again, we're getting deeper into linear algebra, and I haven't even hit chapter 2 yet. I'm augmenting with 0. Do I really need to augment with 0? Is 0 going to do anything when I start row reducing? No, probably not. So after a while, we'll probably drop this guy, and even still call him a homogeneous equation, but 0 times 5 minus 0 is still 0. So it's not going to really change on this problem here, but I just want to be consistent on what we've been doing. This is 0.6 minus 0.9 plus 0.2 is equal to 0, and then 0.4 plus 0.5 PE minus 0.8 PE is equal to 0. Does that make sense so far? Now, crappy decimals, your life, it's a word problem, but solve this thing. What would you do first? If I'm solving this guy, I'm going to go for RREF. What's your first move? Right, we'll do that. Multiply the first row by negative 1 times row 1, replace row 1. Let's go ahead and get that pivot in place. 1, negative 0.4, negative 0.6, augment 0. And this is still going to be 0.6, negative 0.9, 0.2, 0, and 0.4, 0.5, negative 0.8, 0. Now, what's your next move? I'm going to take this pivot and sweep down. This means I'm going to do negative 0.6 times row 1, add it to row 2, replace row 2. And then I'm going to do negative 0.4 times row 1, add it to row 3, replace row 3. Does that make sense? Again, try not to lose anybody, because again, it's the decimal aspect that typically kills people. All right, so here we go. When I do this, this gives me 1, negative 0.4, negative 0.6, augmented with 0. Here we go, that would be 0. Now, this is where your handy-dandy calculator comes in real helpful at. So let me do this so I can make sure that you guys see that I'm really not trying to copy numbers off of problems. I'm trying to do it with you. So this will be negative 0.6. Negative 0.6 times a negative 0.4 added to a negative 0.9, and I end up getting negative 0.66. Does that make sense? Now a negative 0.6 times a negative 0.6 added to a 0.2 gives me a 0.56. And 0 times 0.6, negative 0.6 plus 0, that's still 0, so it never changes the 0 column. Gotta lose you guys anywhere. Now, sweep down, negative 0.4, that gives me 0 there. Negative 0.4 times a negative 0.4 added to a 0.5 gives me a 0.66, okay? And here we go, let's see here, sweep down and kill him off. Now I'm going to do a negative 0.4 times a negative 0.6 added to a negative 0.8. Again, try not to mess up anybody. I get a negative 0.56, and then I get 0 times negative 0.4 plus 0, that's still 0. What do you happen to notice here? This is the same row, except they're negative one of those. So you're right, I can basically, to show the algorithm, take row 2 plus row 3, replace row 3 with it. And what do I end up getting? Row of zeros. 1, negative 0.4, negative 0.6, augment 0. 0, negative 0.66, positive 0.56, 0, and 0, 0, 0, 0. Does that make sense? But you should see that they're the same rows except negative one another. So far, so good. What's your next move? It's all about, it's a chess game, and I'm trying to show you the chess game as we continue to develop our skills. I would, before I do that, I would go for a pivot. I would multiply by 1 over a negative 0.66 times row 2, replace row 2. These are crappy numbers. Crappy decimal numbers aren't going to make it any worse. Okay, so here we go. 1, negative 4, negative 0.4, sorry about that, a negative 0.6, augment 0, 0, 1. All right, here we go. Question. 1 over negative 0.66. That's negative 0.6. Okay, all right, so just multiply that. I'm making him a 1, so I'll multiply by 1 over negative 0.66. So now I'm going to take 0.56 and divide by negative 0.66. And that gives me, oh, crappy decimal. What do I get there? I get a negative 0.84. And you guys are familiar with the bar thing there? The repeating decimal. That's right. We're using all the skills in algebra now. Does that make sense? And 0 times 1 over negative 0.66 is 0, and 0, 0, 0, 0. I got one more move to make. What's my last move? Sweep up from your pivots. We want RREF. That is my ultimate goal. We've got it down to RF, REF. I want RREF. Get that unique solution here. So I'm going to multiply 0.4 times row 2, add it to row 1, replace row 1. And I just did that so I can actually write it down here. Does that make sense? So this would be 0, 0, 0, augment 0. 0, 1, negative 0.84, repeat 0. And here, I will get 0 times 0.4 is 0 plus 1 is 1. That would be 0.4 times 1 is 0.4 plus negative 0.4 is 0. And now, there's my decimal number. I'll multiply it times a 0.4, 4, John, 4, and add it to negative 0.6, right? I get crappy decimal, and I get crappy decimal negative 0.93 repeating. Agreed? And 0 times 0.4 plus 0 is still 0. All right, got it in RREF. Tell me what this means. I want it in parametric vector form. So I'll go for parametric form. Remember, this was in order. PC, PE, and PS. That's the original order that I put my variables in. If you switch them up, that's okay, but you've got to be consistent on who's who to show the relationship. So this tells me that PC minus 0.93 repeating PS would be equal to 0, and PE minus 0.84 repeating times PS is equal to 0, which means what? PC is equal to a negative point, now it will be positive, 0.93 PS. PE would be equal to a 0.84 PS. And to write it in vector form, PS, he's what? He's free, so PS equals PS, which means vectored form, I get this. PC, PE, and PS is actually equal to 0.93 repeat, 0.84 repeat, and 1 factoring out PS. Which means what? Tell me what this solution is actually telling me. A couple of things. Number one, we have an infinite number of solution, consistent infinite for you fancy folks out there. What does that mean? That means I have found an equilibrium spot, but it's infinite consistent, right? So basically, you tell me how much the price of steel is going to be, and then it's going to set what the price of my electricity and what the price of my coal is going to be in terms of creating this economic system. One. Number two, you will also notice something or other that my coefficients here, they are all positive. Okay? So our P bar, or this P vector here, is our equilibrium price. We base it on the price of steel, but the other ones will be fixed off of that. Does that make sense? Why is it being positive important? What happens if one of them is negative? That's my question to you.
Would it be if it's negative that, we're losing money?
None of lose money. This is the price we're setting to create our system. So if I got one of them is negative, just one of them. So, you know, you got a free variable here, PS, and let's say electricity was negative 0.84 or something like that. Well, even though the president and all those folks in Washington would love to have negative electricity costs, I don't think that's going to happen in reality. The reality is electricity is based upon, how do we make electricity? We make it from coal, we make it from oil, we make it from basically nuclear power. That generates quite a bit of electricity, but most of it is actually generated from fossil fuels as our electricity is being generated. We also have water that generates it. We also have wind. We got solar, but you can combine wind and solar together, and that only makes up about, at most, 10% of our electric needs. 90% is coming from oil, gas. It's coming from hydroelectric, and it's coming from nuclear, okay? Hydroelectric is those dams that we put up and they have the big generators coming off of those things as well. But even then, most of it, like 70% of it, is coming from oil, petroleum, and it's coming from nuclear power, okay? So, and none of that is going to ever be a negative cost. So, my point to this exercise is, I said we have an equilibrium system on this one. If one of these guys was negative, I don't have anything, there's no way that, you cannot get, they're gonna have to pay you to use electricity or something like that. No, that's not really the way life works and stuff like that. So I'm also paying attention to not just the fact that I found a solution, but what the coefficients are. They're all positive. If you have one of them that's negative, there will not be an economically balanced system. There's no equilibrium on this system. Does that make sense? Because these represent prices of commodities, and prices are not going to be negative. Nobody's not going to pay you to actually use anything like that. Does that make sense? So I'm not just paying attention to the fact that we have a solution, but because all the coefficients of the PS are positive, means all my prices are positive, that actually tells me I actually found an equilibrium price on this. So there's just more than solving the system of equations, it's understanding what the answer actually means. Does that make sense? Question? Yeah. Right, exactly. Because the goal here is to find that equilibrium price on your model in terms of how these economics within this closed system of, you've got steel, you've got electricity, and you've got coal, and how they're all interacting. This one, there's going to be an equilibrium. When you set one for a particular price, the other prices will be set on how it generates itself. Yes?
So essentially, the question of the problem's question is, there's two of them, right? So it's like find the price for the dual outputs, and then if possible, find the equilibrium prices. Would that solution answer both of those questions?
Yes. So the question, as we said, is, well, we would answer this two ways. Is there an equilibrium price? And if so, what is the model? Okay? Because if you so you can find the solution, and you found the solution to this thing, but when these guys are negative, then you don't get your economic, you're not gonna get about an equilibrium price on this thing. And the answer would have been, no, there is no equilibrium price on this thing. And that would be the ultimate question is there an equilibrium price? And if so, what it is? So if you got one of these negatives, no answer is no economic price, and there's no reason to talk about negative. No one's gonna pay you to, pay you to use coal, or pay you to use electricity, or pay you to use their steel. It doesn't happen like that. And you've gotta create that system that all these coefficients should be modeled because they represent prices of commodities. And those prices are never negative. At best, they'll be free. That would be a zero. Okay.
So the answer is like a ratio, so the price of steel would be
Yeah.
0.84.
The price of electricity is 0.84 repeating of steel, whatever the price of steel is set at. And the price of coal is gonna be 0.93, repeating of what the price of steel is, yes. So there, you found that economic and how the commodities interrelate within the system of your construction, of course. And this kind of makes sense if you've actually worked in any kind of system that, we've got a system where we're using coal, we're using steel, and we're using electricity. And within using that steel, we can create more steel, and so you get some kind of reverberation back into the steel, where you got some, you're using electricity, but with your generators, you can actually create electricity off of that uses of electricity. It's always at a smaller amount, of course. You can't use and create more. That would be utopia for Washington or whatever, but that's not how reality works. I mean, if I'm going to create electricity using electricity, it's going to take a lot more electricity to generate some electricity, but maybe you're creating something else. You get a byproduct of electricity. That's a benefit. You won't have as much as what you put into it, but maybe you get some of it out. Same idea with the steel. But with coal, you're burning up all the coal. There's no coal byproducts coming out of it. It's showing up in the atmosphere and burning off and stuff like that. Okay. Does that make sense? Again, economic models. Now, one more. See if I can go for another model here. This is your network system. Okay. The network system, so for all you computer science majors out there, which I know is exciting for you guys, there is, but I like to look at this more of a civil engineering problem, okay? Because every time I drive over here to UNC Charlotte, and I stop off at the stoplight over there on 485, getting over here, I really want to take some of these civil engineers who are actually in charge of the monitoring of the red lights and goes and stops and stuff like that. These people clearly have not done their math on figuring out the best time to let traffic flow versus putting the stoplight on there, which stops the people coming in off the interstate, which creates traffic jams, okay? This is kind of the same system here. And again, I'm stealing a problem out of your textbook here, and it's basically called the network flow type thing here, and I just redrew this thing. And this is an example of something in Baltimore, so we can go pick on those guys. All right, so this is their model here. But to create this network, so what I'm after is the diagram of the network and how things interrelate here. All right, so network contains nodes and branches. So you got, and direction is everything, coming in versus going out, stuff like that. So with this system here, network contains nodes and branches. Assumption, this is very important. We're talking about traffic. Inflow is equal to outflow. Now, I know we all see the car sitting on the side of the road, and he didn't quite make it through the system here. Let's avoid him, because AAA is coming. But inflow is equal to outflow, okay? So that's what's going to set up your equations from each node. So each depends on the sources, dead ends or sources in your network. So you got dead ends and you got sources. So I'll talk about that in a second. So at each node or junction, and don't forget, you got at each node or junction, you got inflow is equal to outflow. Don't forget this one. And over the entire network, inflow equals outflow. This is where your equations are going to come from, okay? So, traffic patterns. And now I've tried to label these guys, so let me describe each one of them, and then we'll talk about the equation. So here's my traffic pattern here. So let's look at node A, for example. We got 500 cars on any given days coming into node A, okay? What's going out? And we also, over on this direction, coming east, we got 300 cars coming in. What do we got going out? We got a variable x1 coming out of node A, and we got x2 coming out of node A. Does that make sense? Look at node B. What's going in? We got X4 is going in, the amount of X4, we got X2 coming in, what do we got going out? X3 is going out and 300 is going out. So at these particular spots, we've actually put one of those little radar detector things. You remember those little things you drive over? It's counting how many cars go over the little things. So we do this kind of stuff all the time. This is how we set traffic light patterns and understanding the flow of traffic. This is classic DOT, also the civil engineers and all this other good stuff, being able to solve this type of system of equations. C, node C, what do we got coming in? 400 cars coming in from the east, 100 cars coming in from the north. What do we got going out of intersection C? We got X5 variable, we got X4 variable going out. And then node D, what do we got coming in? We got X1 coming in, we got X5 coming in, what do we got coming out? Just 600. We took that count. So there's two things of intersection coming in, so cars coming from the north, coming from the west, and going out, because you don't have an intersection here, just can go out 600, we monitor that, 600 going out. The other thing is this, total. How much is going into my system, and how much is coming out of my system? What do we got coming in? Coming in, so this is the system. We have 300 coming in. You with me? We got 500 coming in. And we got 400 coming in. And we got 100 coming in. You see where I'm getting this from? The arrows going into the system all along the branches. What do we got going out of the system? We got 600 going out. We have X3 going out, and we got 300 going out. So you're looking at the entire system. So this is the outer fringe, what's coming in and what's going out in terms of equations. So I'm going to slide this to the top. So all we need is this thing, and I want to come up with the equations. So node, let's look at node A, for example. Again, remember, this is how the equations come up. Input must be equal to output. So what's going input of node A? Input of node A is we got 500 plus 300, right? That's equal to what? X1 plus X2. There comes my first equation. Don't worry, I'll clean them up and make them look good in a second, but input equals output. Node B. What's going into node B? Input is what? X2. What else? Plus X4. That's equal to X3 and 300. Does that make sense? I'll lose you guys anywhere in my analysis. Look at node C. Node C is here. What is the input? Coming in is 400 and 100. 400 plus 100. That's got to be equal to what's the output? X5 and X4. And X5, again, the arrow makes all the difference. So X4 is going out plus X5 is going out. Does that make sense? Look at node D. Node D, what is the input? X5 is an input and X1 is an input. So this would be X1 plus X5. What is the output? There's only one direction out, and we monitored that, and we got 600. Does that make sense? But there's one more equation. This is where most people screw up. Okay, and this one is your total in has got to be equal to the total out of your system. So there is one more equation on this thing, okay? What are the things going into your system? Going into my system. There is 300 here. I'm going to go, there is 500 down here. There is, that's going out, 400 going in, right? There's another 100 going in, okay? What is, these are going out. What is going out? Starting here, what's going out? In, out is 600. Does that make sense? Going in, going out is an X3. Out is a 300. Does that make sense? Sorry, I can't see that one. Does that make sense in terms of don't forget this big equation here? So now, we got these equations. So now let's see if we can't write ourselves a system of equations here. So, here we go. Systems of equations. Let's start with equation A. X1 plus X2, leave a little space over here, is equal to, what is 500 plus 300? I can do that math out of a calculator. That's like 800. Does that make sense? B, now try to line these guys up. So I'm gonna pull everything to one side. So this would be X2, let me put B over here. X2 minus X3. You see I pulled him to the other side, plus X4. That's gonna be equal to 300. I'll lose you guys there. I'm trying to pull all my variables on one side and move my constants to the other. So I'm doing this juggling of the equation because I'm trying to create this system of equations here. C. I want to pull, when it doesn't matter, I pull over here. This will be just X4 plus X5, just writing it the other way, would be equal to, what is 100 plus 400? 500. No D. X1 plus X5, as I do try to line these guys up, that would be equal to 600. And there's one more equation, and that would be your total equation, right? What do we got here? I've got, oh, time for a calculator now. 300 plus 500, that would be like 800. I can do that math. Plus 400, 1200, plus 100. Does that make sense? But then I've got 900 over here. So I'm going to subtract off 900 because I'm moving it to the other side. And that gives me 400. Now, so I move this to the other side, and that was equal to what? X3. There was only one variable in my total equation. Does that make sense? So I put those numbers together, and this was 900, and so I subtracted 900 from both sides to get all my costs together. So I'm juggling this stuff as I go. So this ends up becoming my model now. They'll lose you guys anyway. Solve it. Okay? So solving this guy would give me this kind of a matrix. And I like to, when I'm doing these big matrices, because this one's kind of big, I like to kind of put my variables at the top here as such, because it's easier to line up. So this is 1x1 plus x2 is equal to, and we got 800 over here. Set equation is 0x1 plus x2 minus x3 plus x4. That was equal to 300. Next equation is 1x4 plus 1x5 is equal to 500. I have here x1 plus x5, that's equal to 600. Go down and I got one more. X3 is equal to, what was it? 400. Well, that's kind of nice. I knew X3's got to be 400.
600? That's 300 plus 500 plus 400 plus 100. That's 1,300.
Okay.
No, okay.
400? Yeah. Well, okay, so put my zeros in there. 0, 0, 0, 0, 0, 0, 0, 0. Good. 0, 0, 0, 0, 0, 0, 0. Okay. Now, I've got my matrices. Okay? So, what would you do to solve this guy? Now, I'm going to save some time in this because I'm trying to show the example and I want to do more things here. But I'm going to go for this guy, I'm going to go for RREF. Pivot, sweep down, so clearly I'm going to kill this guy off. Then I'm going to make this a pivot. It's already got zeros below it. Then I'm going to row swap and then make that a pivot, zeros below it, and then make him, you understand. So I'm going to show you guys something or other on the calculator. Question for you. How many variables do I have here? 5. What do I have? 1, 2, 3, 4, 5. Okay. So it's not over-determinate, it's not under-determinate. I got the exact same number of equations as variables, okay? So what size matrix is this guy here? Again, showing you this on my calculator just to save some time. What size matrix is this guy? 5. All right. So second matrix, edit, I'm edit A here. You said it's 5 by 6, right? What are my numbers? On my mark, get set, and go. 1, 1, 0, 0, 0, 800. Equation 2 is 0, 1, negative 1, 1, 0, 300. Equation 3 is 0, 0, 0, 1, 1, 500. And 4, let's see here, 1, 2, 3, 4, is 1, 0, 0, 0, 1, 600. And equation 5 is 0, 0, 1, 0, 0, 400. Right. So this is what I always do when I do my calculator. If I'm going to cheat, quote unquote, or check my answers, okay, second quit, call it matrix A, and just look at it. And make sure I type them in right, because I am notorious for doing this thing so fast and losing a sign here. And if I mess up, and I got a doctorate degree, you know what you people do? Awful. All right, so 1, 1, 0, 0, 0, 300, 0, 1, negative 1, 1, 300, 0, 0, 0, 1, 1, 500, 1, 0, 0, 0, 1, 600, 0, 0, 1, 0, 0, 400. Now, what's the beautiful math? Okay, go to second matrix, go to math, scroll down to RREF. What do you think that stands for? Reduced echelon form. On matrix A, got to tell what matrix it is, and it gives me the answer. So, if we did this right, turning the page over here, RREF, we got this. 1, 0, 0, 0, 1, augment 600. We got 0, 1, 0, 0, negative 1, 200. We've got 0, 0, 1, 0, 0, 400. We've got 0, 0, 0, 1, 1, 500. And we've got 0, 0, 0, 0, 0, 0. We've got a row of zeros, which tells me what? Again, this represents x1, x2, x3, x4, x5. Please tell me what the deal is. Okay? So again, parametric vector form. So what do we get? We get x1 plus x5 is equal to 600. We get x2 minus x5 is equal to 200. We get x3 is equal to 400. We know exactly what's going on in x3. We get x4 plus x5 is equal to 500. Does that make sense? 1, 2, 3, 4. You have 4 pivots. Does that make sense? Infinite number of solutions. So there's a parametric vector value equation here. x1, x2, x3, x4, x5. Remember x5, he's going to be free. He'll be equal to x5. Does that make sense? So as I write this down, this would be equal to, move this to the other side. This is negative 1. Move this to the other side. This will be 1. This is 0 because there is no x5. This x4 moved to the other side is going to be negative 1. And x5 equals himself. That'll be 1 times x5 plus 600, 200, 400, 500, and x5 equals x5, that is 0. So this is your parametric vector value form. So x5 is free, so please tell me what this actually means. All right, so let's go back to, I'll put it up here, sorry about that. Go back to my big picture here. What did I do with my big picture? It's this one right here. There's my big picture here, so tell me what's going on. So for this particular set of intersections in Baltimore, x5 is going to be my free variable. So I need to analyze what's going on right here. Well, I circled it. And here in x5. So if I can figure out what's going on in x5, I can tell you the inflow and outflow upon the traffic in all of these roads. Does that make sense? And these one-way streets and stuff. Once I figure out what X5 is, I can put it under here, and I can figure out the relationship between X1 all the way down to X5. You tell me what X5 is doing, I can tell you what the rest of these intersections are doing. Does that make sense? So that's a wonderful system so that, thinking about it from a DOT perspective, I arbitrarily monitor these systems on a Monday through Friday or even the weekend perspective, and I basically, all I need to do is analyze what's going on here, this particular street, and to count the number of cars in any given day, and then I can figure out the flow of traffic through the rest of these roads, X1 through X4. Does that make sense? A very important, you see, my goal here is to show you the power of linear algebra and what it can do for you besides just solve systems of equations. These systems of equations mean something or other. This is DOT stuff that they need to work on a lot better around here, but you get the idea of how this stuff is actually utilized and whether you can solve the system or is the system going to be inconsistent. Maybe you don't have enough variables or enough information on a particular system. You need to go out there and figure out what's going on. So there's a lot of applications of this stuff. I just showed you two of them, classic DOT style and economic system in terms of, basically generating and constructing things like coal, electric, and steel and how those interact within closed systems as you generate stuff. So this has got great, great potential. So from here, let's look at section 1.7, and I got like 1 minute to do it, but I wanted to go over these guys because they were actually very important. So with that, and I'm going to put down one definition here, and then I'm going to let you go, and I'll finish up 1.7 and 1.8 next time, because this is kind of a short section here. It's a definition. Section 1.7, we're going to be talking about vectors again, and we're talking about something called linear independence. Okay? Linear independence, one big definition. A set of vectors, V1, V2, out here to VR, little vector symbol above them there, okay, of Rn. What does Rn stand for? R4, R3, it's the dimension of the vector. This is the n is the number of component in each one of these vectors. So if it's R3, each one of these vectors is first, second, and third component. R4 is 1, 2, 3, 4 components in each one of the vectors, okay? This is some vectors of Rn here. These guys are linearly independent if for C1, C2, C3, C4, CR actually, scalars. Scalars means constants. In the real numbers, we have if C1 times vector V1 plus C2 times vector V2 plus plus CR times vector VR is equal to the zero vector implies that C1 equals 0, C2 equals 0, CR equals 0. They're all equal to 0. Okay? And if there exists a CI that is not 0, then we say the vectors linearly dependent. So we're talking about linearly independent versus linearly dependent. So what I mean by that is this. If there is a constant out here that's not 0, probably a couple of them, but at least one of them that's not 0, and we're setting equals 0, you can take that particular vector, move these vectors to the other side, and you can write one vector as a, quote, linear combination of the other vectors. That's called linearly dependent. And you can write one vector as a linear combination of other vectors. If you cannot, the only way you cannot is all the C's have to be equal to zero. The only way zero is equal to the zero vector is all the coefficients have to be zero. Then we talk about these vectors being linearly dependent. This is gonna be a very important idea down the road and talking about the relationship of vectors and what they span. So let's focus on this definition and we'll pick this up next time. So study hard. I'll see you guys tomorrow. We'll finish up 1.7 and then move on into section 1.8. And there's only 10 sections in here, 1.9, so we're cruising very close to coming for your next test. See you guys then.